can still see people coming in, but I'll get going and offer a very warm welcome, too warm a welcome, really, to everyone who's here sheltering in the last Balliol Online Lecture for this academic year. It's been such a pleasure to host these events. One of the real silver linings, I think, of the pandemic and innovation for the college to put these on a pretty much monthly basis. And we're already starting to think about the lecturers for next year. And it's great to see so many familiar and new names I can see in the audience for this lecture. So welcome to you all, whether it's your first or one of many lectures that you've attended with us. And I'm delighted to introduce this month's speaker, who's Jason Lotay, Professor of Pure Mathematics and Tutorial Fellow at Balliol. Jason joined Balliol from UCL in January 2019, when he succeeded Professor Dame Frances Kirwan as Tutorial Fellow when she took up the civilian chair of geometry. And I think, Jason, this is pretty much your last duty before you go off for a year to take up a visiting professorship at Berkeley for the next academic year. So thank you for doing this just before you depart. And we also have on screen Rhiannon Savage, who's a current Balliol doctoral student in maths. And Rhiannon's one of the graduate teaching assistants in maths, so integral part of the undergraduate teaching team for Balliol maths students this year. Rhiannon will be moderating and reading out the questions, which are very much encouraged, and you can use the Q&A box at the bottom of your screen to submit those, and you can submit them as the lecture goes on, and then we'll make sure that we have them all in good order, ready for the Q&A afterwards. So the format today will be around 40 minutes for Jason's lecture, and then up to 40 minutes for the question and answer, which will follow directly afterwards. And with that, I'll hand over to Jason and what is, I think, a particularly auspicious month for Balliol mathematics. And maybe I'll leave you to say a little bit more about that in your introduction. So thank you very much all, and welcome.
Thank you, Richard, for that very kind introduction. And yes, indeed, it is a very auspicious time for Balliol mathematics. We have one of our current doctoral students, Jared Lippman, has proved a conjecture from the 1980s that had stumped mathematicians since that time. And it's amazing for someone so early in their career to tackle something so challenging and to succeed. And in even bigger news, one of our former doctoral students here at Balliol, James Maynard, has been awarded the Fields Medal, which is the highest possible award in mathematics. It's awarded once every 4 years, and if that's not enough, you have to be under 40 years old to win it. So it's really an amazing honor to do that. So today I want to talk about mathematics. I want to talk about knotty problems. So these are some problems that are interesting to me and to other researchers around the world in mathematics, but I also want to link it to the students too, because this is not something that's just part of research mathematics. It's very much embedded throughout the whole of mathematics teaching here at Balliol. So let's begin by saying, well, what is a knot? What is a knot? Well, so this is something that's very familiar to you in everyday life. For example, if you have a piece of rope like this, then you can tie a knot in it. Now, in mathematics, this isn't quite what we mean by a knot, because if you had just a piece of rope like that, you could always just untie it again. So for mathematicians, what we do is we imagine taking that rope and fusing the ends together to create a closed loop. And in that way, you can't untie the knot without cutting the rope again. And so you can detect how complicated your knot is. Now, knots, maybe in your life you find knots very annoying if it's your tangled up cables, but they can also be very helpful. For example, if you do climbing, here's a more complicated knot that would be very useful to you. But they can also be very beautiful, I think, and they appear in artwork in many different places, perhaps most notably in Celtic art. So here we have a Celtic knot made out of string, and here it is on a Celtic cross here. And the knot is not just used purely for its decorative use, it's also symbolic, the fact that it's a closed loop that goes round and round and never ends. This is a symbol for the eternal, And of course, one can combine both utility and beauty and link it to mathematics. For example, in the following way. You can create out of knots and out of pieces of string, one of my favorite mathematical objects, which is the dodecahedron. So this is one of the Platonic solids. It's a 12-sided shape made out of pentagon faces. And I think it's it's a fascinating thing. I could talk for hours about this, but we're going to focus on knots today. So it's all well and good that now we know what knots are and they're beautiful things and very useful, but what is the mathematics behind them? What's the interesting question? And the key question in the study of knots can be summarized as spot the difference. So in other words, if I give you two different knots, how can you tell whether they are the same or different? And again, this is something that you're probably quite familiar with in real life. If you have a huge mess of cables, it's not really clear whether they're just tangled up, so if you just gently pull on them, they'll eventually all come apart, or whether one is really tied around another one, and so something has to be undone in order to get back the cables. So here's a little example for you. I have the following two knots. So I have this one, which is very simple. It's the simplest possible knot you can draw. There's no knot at all. And I have this one, which looks extremely complicated. And so let me let you think about that just for a few moments and say, well, how on earth would I tell whether this one is different from this one or whether it's the same? And it's not obvious. So let's see whether it's true or not. Well, let's start off with that untangled knot, the simplest one. Then we can put in a little twist like this, and you create a little figure eight there. You can twist it again, and now it looks knotted, but it isn't. All I've done is pulled that one through, and I haven't created a knot at all. And I can keep twisting and tangling until eventually I end up back at the knot that I started with on the previous slide. So in fact, even though this one looked very complicated, it is actually not a knot at all. It can be completely undone. Now, the problem is, how would I know what moves to make? How would I know how to reverse this process to get back? And that's very complicated, and that's the essence of knot theory. One of the questions is, how do I detect when two knots are the same or different? So knots are very important in mathematics, and we need to have a language to talk about them. So this one we've seen before, it's the simplest possible knot. And so we have to give it a name, and the name that was chosen is the unknot. I think this is to avoid saying not knot, which is, or not a knot, or something like that. And so we put unknot. You can think of this like the number 0 in some sense, the unknot. And you can ask which one is the next most complicated. And that's this one. So this is if you just put a single twist in your rope and then fuse the ends together. And that's called the trefoil knot. And you can keep going. You can ask what is the next most complicated knot that you can write down. And that's this one, which is the figure 8 knot. And you can keep going, and you get more and more complicated knots, for example, like this one. So you can keep listing them, and you can say, well, all right, but you could never tell if I gave you, say, this one in this form, or I gave you a more complicated version, how would you know whether it was the same or different? But it's not just useful in mathematics. In fact, this listing of the knots came out of an idea of Lord Kelvin, who had the idea that atoms, molecules, these fundamental building blocks of nature, were built out of knots in the ether, which was this sort of substance that they imagined that we all moved through. So that knots in the ether thing didn't turn out to work out so well, but nevertheless, it compelled the mathematician Tate to try to list all of the knots and then try to connect them to physical objects. But of course, although that idea did not survive, of course, this has come back into popular science because we now have the theory of high energy physics known as string theory. And string theory is a way to understand the fundamental objects in nature using little loops, which we would think of as strings. And of course, those can be knotted. And so it's not so shocking, perhaps, that knot theory has a connection to string theory, therefore to our physical world, and possibly to a way to understand the sort of fabric of our universe. But knots also appear in other places in art and science. So perhaps one of the most famous examples of this is the so-called Gordian knot. So the story goes, as I'm sure you know, that in somewhere in ancient Greece, I think it was Phrygia, there was no king, and so then they created this puzzle, which was a very knotted piece of rope or piece of other material fastened to an ox cart. And they said, whoever can untie this knot and so get the cart would then rule the kingdom. And this was an incredibly challenging problem. And depending on which story you read, this was solved by Alexander the Great in one of two possible ways. Either he simply sliced through the knot, that's one way to solve the problem, or he just untied the peg that was fastening the ox cart and therefore rendering the knot totally useless. Either way, he cheated. I mean, he didn't actually solve the problem, but it's where that phrase, cutting the Gordian knot, comes from. And so this is a very popular thing that you probably heard of to do with knots. Something that you maybe haven't heard of is a biological place where knots appears, and that is in the realm of zoology and in the study of a creature called the hagfish. So the hagfish is a creature that lives near the bottom of the ocean, and it has this very peculiar habit of tying itself in a knot. So it's not a very attractive creature, but here it is a representation of it tying itself in a knot. And it does that because it uses it as a mechanism to feed. It generates some force, so it's able to eat using this knotted behavior. Sticking with the zoological theme, there is another kind of knotty animal, which sometimes goes by the name of the Gordian worm. So I haven't shown you a picture because it's a fairly hideous thing, but it's a very, very small, at least thin worm, but it can be very, very long. And it's a parasitic worm that has things like grasshoppers and crickets as a host. And it has a very unusual habit. So obviously, typically, it lives inside the host and does its usual thing. But occasionally, it wants to reproduce. And when it does so, it has to get to water. So, of course, crickets and grasshoppers, they don't want to go to water. And so it alters the brain chemistry of the grasshopper so that it goes and drowns itself. And in that way, the worm is able to escape and to breed. It's amazing, like what wonders there are in nature. And if I mention to you the word knot or string or strand in connection with biology, you may have been drawn to the idea of DNA. So here are some electron microscope images of some DNA strands. And you may be able to see here on this one that it's knotted, right? Here the strand goes above and under. In fact, this is a knotted DNA strand. And one could say, okay, that's fine, that's just maybe coincidental. But in fact, it turns out that there are links between the biological mechanisms at work in DNA and the way in which the strand is knotted. And that is something that's being studied as a collaboration between mathematicians and biologists. So I've explained to you some of the ways that knots appear in nature. In fact, knots have very recently appeared in the publication nature. So this was work of two of my colleagues in the Mathematical Institute. Here they are, Andras Juhas and Mark Blackenby, who worked together with two scientists from Google DeepMind. And they used machine learning techniques to uncover a surprising link between various properties of knots. It's a surprising collaboration between machine learning, so computer science, computer engineering community, and mathematics. And I think this hopefully will prove to be the start of a very fruitful new collaboration. And you may have noticed in these very nice pictures of my colleagues that there's this beautiful Radcliffe Observatory in the background. In fact, this is taken from the roof of the Mathematical Institute. I encourage you to go to the roof of the Mathematical Institute if you can. It's a very nice place. There are roof gardens up there and nice views. And in fact, if you go to the place where this picture was taken, you will see the following sculpture, which is a representation of a certain knot, in fact. Here, and you can see a little bit of the roof garden. There's a picture I took myself when I went up to the roof garden. It's a nice place to go. Okay, so now what I would like to do is explain to you what are the connections between knots and the maths that we do here at Balliol. So is there a link between knots and Balliol? I mean, there's no reason why there should be, but in fact there is. So one of the a famous alumnus of Balliol, a former junior research fellow, is Peter Kronheimer, pictured here, who is one of the certainly a world famous mathematician, and he has solved some of the key problems in knot theory. He has made some absolutely fundamental contributions to the subject, and so we have a clear link to knot theory here at Balliol. Now, an interesting coincidence is that Peter Kronheimer is actually a mathematical brother of Dame Frances Kirwan that Richard mentioned at the beginning. Another, of course, very famous Balliol DPhil student and then fellow. And as I said, they're mathematical siblings because they had the same DPhil supervisor, who is the late, great Sir Michael Atiyah, pictured here. And he is, if you've not heard of him, he is certainly one of the most influential UK mathematicians of the late 20th century, in the second half of the 20th century. Just absolutely phenomenal figure who did amazing contributions to many parts of mathematics. And his legacy certainly lives on. Now, you may have noticed in this diagram that there's a little corner here missing, a little space, and perhaps you may have guessed who will appear in that space. Yep, it's me, because I am now, of course, here at Balliol, a successor of Frances Kirwan. And in fact, I'm a mathematical great-grandson of Sir Michael Atiyah. So the supervisor of my supervisor was Michael Atiyah. And now I am working on some knotty problems. So hopefully I can connect this diagram and link myself to Peter Kronheimer here in the top left. Now, of course, I've put a dotted line here because I feel kind of ashamed being on this, or embarrassed, I should say, to put myself on a slide with such great mathematicians. But I hope that I can make some, at least small contribution to the realm of knot theory and hopefully cement my place a little bit more on this slide. So I've explained how knots are connected to Balliol and to research, but what about our students? Well, of course, we might be accused of tying our students in knots, but that's not really what we do. We work very hard to explain away their difficulties and unlock the mysteries of the subject. But the question is, do students see knot theory at all during their course? Well, even from the first year, they will study geometry. And when they study geometry, they will see curves in 3 dimensions, such as this one. And this is a knotted curve, or potentially knotted curve in 3-dimensional space. The sort of thing they would study. So geometry is something very familiar to all of us. We understand what it means, study of shapes in space. But in the second year, the students study a different topic, which is called topology. And the slogan is that a topologist is someone who can't tell the difference between a coffee cup and a donut. And so the reason is this. So imagine that my coffee cup was made of plasticine, then I can deform it in this way until eventually it becomes the donut. And so a topologist would say, well, then all of these objects are the same thing. I can imagine them as all the same thing because I can continuously deform from one to the other. So geometrically, they're different, but topologically, they are the same. And that's the same with knots, right? We had the original, remember I had that picture of the very simple knot and the very complicated one. Geometrically, those are different, but topologically, they're the same, because as I smoothly untie it, I will eventually get back to the unknot. And so clearly, knots lie in the realm of topology. During the third year, the students will develop their understanding of geometry and topology until the fourth year, where they'll actually see knot theory itself and see how it connects to algebra. So algebra, as we know, is the study of equations. It's one way to think about it. It's perhaps these simultaneous equations, like x squared plus y squared equals 1, x squared plus y squared plus z squared equals 1, and x squared plus y squared plus z squared plus w squared equals 1. But they will also see how knot theory is connected to analysis. So what is analysis? In the mathematical language, that means studying sequences and series, so adding up lots of numbers in a row, infinitely many. Calculus, so differentiation, integration, measuring the rate of change and the areas under curves. And then if they get on to research level study of knots, they may see how knots are connected to differential equations. So that's what I've written down here, is a certain differential equation. In fact, it's a very famous one for those of you who know what it is. This is the heat equation, the way in which heat dissipates around a room. Okay, so now I want to try to explain to you what is the knotty problem that I want to study. And to do that, I'm going to have to teach you a little bit of maths. So let's start off and imagine that I have a point on the floor and I have a meter-long ruler, say, on the floor. And I fix one end of the ruler and I ask, so here's one end of the ruler and here's the other end, and I ask, if I swizzle that ruler around and I keep it's always a meter length, then what shape will I trace out on the floor? And I'm sure that you know the answer, and the answer is going to be a circle. So let's do the same thing now, but rather than having my meter ruler on the floor, I put it up in space. So just up I just hold it up and I trace it around, keeping one end fixed, but allowing it to move in all 3 dimensions. And I ask, what shape will I trace out? And the answer is, I will trace out a sphere. So in the first case, I traced out a circle. In the second case, I traced out a sphere. Now, if we think about the sphere, it lives in 3-dimensional space. But if I pick a point on the sphere, say this one, then I notice there are only 2 directions I can go and stay on the surface of the sphere. I can either go up or down or left and right. And so that means that it's really a 2-dimensional object living in a 3-dimensional space. And so that is we call it the 2-sphere for that reason, because it's 2-dimensional object living in a 3-dimensional space. And here, if I pick this point on the circle and I move back and forth, then that's the only thing I can do. I can't move up and down because I'll leave the circle. I only have 1 dimension to move in, and so I call that the 1-sphere. And in fact, I can do the same trick. I can take my 1-meter ruler and take it, well, what did I do here? I left it on the floor, so that was in 2-dimensional space. Here I picked it up, that was in 3-dimensional space. Now I take it into 4-dimensional space and I twizzle it around and I say, what shape will I sweep out if I do that, holding one end fixed? And the answer should be a three-dimensional object, which I call the three-sphere. Logical sense, that's the sequence. But that's all well and good. I can explain that to you in that way, but it doesn't give you a good sense of really what does it mean? What does it look like? Well, another way to think about it is for the one sphere, that is the solution to the equation x squared plus y squared equals 1 if I use x and y coordinates, right? That's something that you remember probably from school. That's a consequence of Pythagoras' theorem. So Pythagoras' theorem also works in 3 dimensions, and it will say that the sphere is the solutions to x squared plus y squared plus z squared equals 1, where x and y and z are the coordinates in 3 dimensions. So if I have 4 coordinates, then the 3-sphere should be the solution to x squared plus y squared plus z squared plus w squared equals 1, which of course you've noticed are the 3 equations that I had on the previous slide. But again, that doesn't help a great deal in to imagine what it looks like. So let's go back to the 2-sphere and think about lines of latitude on the 2-sphere. So if I take lines of latitude on the 2-sphere, they are 1-spheres, they're circles. And they start out very small at the South Pole. They get bigger and bigger and bigger until I get to the equator, which is the biggest one. And then they get smaller and smaller and smaller again until they disappear at the North Pole. And so we can see that the 2-sphere is actually built out of 1-spheres. I start from a point, I get a bigger and bigger 1-sphere until I get a biggest one, and then I go smaller and smaller and smaller again until I get back to a point. And the object that I trace out will be the 2-sphere. So the 3-sphere should be the same thing, but I replace each of these lines of latitude with a 2-sphere. And so it will look something like this. I have a smallest 2-sphere that gets larger and larger and larger until there's a largest one, and then they get smaller and smaller and smaller again, disappearing off to a point. And the thing that I trace out will be the 3-sphere. There you go. So now you have lots of different ways to think about the 3-sphere, and in particular, a visual one. And I thought this was pretty clever. I thought that I'd thought of something quite new and quite interesting way to think about it. But it turns out that somebody else had thought of this way of describing the 3-sphere a few years before me, and that person was Dante. So Dante, in the Divine Comedy, when the traveler is moving through Empyrean and he reaches the middle of the journey and looks back at the earth and up into the heavens, he says, "Well, I look back at the earth, I see spheres in front of me getting smaller and smaller and smaller. And I look up into the heavens, I see spheres ahead of me getting smaller and smaller and smaller." And so what he's describing is that the total universe is a 3-sphere. That is what Dante is saying. And if you don't believe me, there is an article here, Dante and the 3-sphere, which explains more precisely the language in Dante's Divine Comedy that in fact justifies what I just said, that he views the universe as the 3-sphere. In fact, there are lots of connections to knots in Dante's Divine Comedy, as I learnt from our Dante scholar here, Elena Lombardi at Balliol, and she explained that knots appear a lot in Dante's work, and he even says that God is a knot. And this is a very enigmatic statement. It's not quite understood what Dante means, and still forms part of current research to understand what is the meaning of that statement in Dante. So a cute connection between knots and some medieval Italian literature. Okay, but back to the 3-sphere. Now, what I want to do is explain another link between the 3-sphere and the 2-sphere, and that's the idea of projection or wrapping. So this is something that you're familiar with. If I take the regular 2-sphere and I project it, if I take a point, I can then unwrap it to become flat. So I take my globe and I pick my favorite point, in this case, the North Pole, and then I can unwrap, like a Terry's chocolate orange, my my two-sphere until it lies flat and becomes two-dimensional, which we know it is. It's a two-sphere. And you see that the lines of latitude here become circles in the plane. So we can also reverse the process. If I have a curve in the plane, then I'll get a curve on the two-sphere when I wrap up the plane. So I want to do the same thing with the three-sphere. So if I take a three-sphere and pick my favorite point, I should be able to unwrap it and I get some three-dimensional object. And that three-dimensional object will look something like this. So this is a representation of what the projection of the three-sphere would look like in our world, with 1 point removed. So I could look at this all day. It's a very beautiful picture of what's happening. And it shows that it's much more complicated. And you can see that there are curves in here. So it's a slightly less good picture, but you can see there are some loops inside this picture. So if I'm given one of these loops, for example, I'm not, then when I wrap up the world and create the three-sphere, my knot will now live in the three-sphere. That's the key point that I want to make, is that now I can equally think of knots, not living just in my hand, but I can think of them living in the three-sphere. And that's a very important point of view. So what is the precise question that I want to answer? So it's got something to do with knots and the three-sphere. And the connection is to do with knots and surfaces. So what do I mean? Well, let us start with our favorite knot, the unknot. Now I can see that this knot bounds a surface, meaning there is a surface which has that knot as its boundary. And I can draw it. It's just that. It's just this orange disk here. And this orange disk has this blue thing as the boundary. And what this means, because I can find a disk, I call a knot of this type a slice knot. When I can find a disk which has the knot as its boundary. Now I should be slightly careful, because I said I can think about knots in two different ways. I can think of them in real world, or I can think of them in the three-sphere. So really what's happening is I'm thinking of my unknot as living inside the equator, say, inside the three-sphere. So of course I can't really draw the three-sphere so easily, so I'll just replace it by the two-sphere. And then what is this orange disk that I want to draw? It doesn't live inside the three-sphere, it lives in the interior, so in 4 dimensions. That's where this disk lives. And so I can draw it as follows. So that's the disk that I want to draw. It's a disk that lives inside, in the interior of the three-sphere. And that's why we call it a slice knot, because you imagine that I take something and I slice through the three-sphere, and when I do that, I'll see this slice, this oval here, and that will be my disk. And that's why I call it a slice knot. Now, of course, there are lots of surfaces that live inside in the interior of the three-sphere in 4 dimensions that have that red curve as the boundary. For example, this one, I can add a handle and create this that thing. That's actually a donut shape. And so the natural question isn't really which one can I find, but which is the least complicated one I can find. That's really the question. And that was the question that was answered by Cronheimer. So Cronheimer solved this problem for a particular class of knots. And that was a really fundamental result in the field, because it is in general very difficult to determine what is the least complicated surface you can find bounding your knot. In particular, it's very hard to determine when something is a slice knot. That's an extremely hard question, and nobody knows the answer. Okay, so that's one type of knot, and that's one connection between knots and surfaces. Here's another one. So these are the so-called ribbon knots. So here, the knot is this dark red curve which is the boundary of this purple ribbon. And that's why it's called a ribbon knot. So a ribbon knot is a knot so that when you thicken it out in this way, you get something which looks like a ribbon. So it's a surface where you can sort of cut little holes in it and then you can make it out of ribbon. That's the sort of idea. And so this thing, this surface that I've drawn, this ribbon, this really lives in our three-dimensional world. So if I go back to my picture over here, where would the purple surface be? It would be this one. This would be the purple surface. It would be the thing that lives actually on the surface of the three-sphere. That's where it would live. And so we see, in particular, what has happened. If I took the unknot, then on the one hand, I can find this orange disk, which has the knot as its boundary, but I can also find this purple disk that lives inside the three-sphere that has the knot as its boundary. So that means that the unknot is both a slice knot and a ribbon knot. It has both properties. And that's quite strange because slice knots, I said, are very hard to detect. Ribbon knots, on the other hand, are very easy to understand. These are actually very simple objects to describe. It may not look like it, but they are. And so let's have a look at some other knots. For example, this one, known as the stevedore knot. This knot has the property that it is both slice and ribbon. Curious. So that one has the property that it's both slice and ribbon as well. Okay, let's have a look at another knot. This one, which is called the granny knot. I don't know why, but it is. And we say, is this one a ribbon knot? Because that's easy to check. And the answer is no, it isn't. Is it a slice knot? That's a harder thing to check. In fact, it isn't one of those either. Okay, so now I'm spotting something of a pattern. Maybe if I take a slice knot and I take a ribbon knot, maybe those two things are always the same. Maybe those are always the same thing. And this was a conjecture that was asked in 1962 by the mathematician Fox. And he asked, are slice knots and ribbon knots the same? And his conjecture is that they are. And this is an open problem. It's been around now for, I guess, 60 years, and we don't know the answer. It's a very difficult problem, and we don't know. And this is one of the knotty problems that I'm interested in. And just to, in the last part of my lecture, I want to explain how might you try to answer this question? What might you try to do to try to tackle such a problem? What kind of maths would you want to use to do this? And the answer is to think about something from real life again, and that's soap films and soap bubbles. So the property that a soap film has is that it's trying to minimize its surface area. Because of surface tension, it's trying to minimize its surface area. So for example, if you take two loops of wire and you dip them in soap and you pull them apart very gently, then you will get a surface that looks like this, made of soap. And you're always going to get the same shape. You always get the same shape because if you want to minimize the area, there's only one answer. You're always going to get this. You do it carefully and pull them apart slowly. So that's a very nice object that you can describe. It's called the catenoid. But these are unknots, right? So that's not very interesting. So let's take a more complicated piece of wire and dip it in soap and see what happens. So here I've taken a knot, well, not me, somebody else has taken a knot and dipped it in soap. And now you can see there's something more complicated going on. In fact, what knot is that? It's the trefoil knot, actually. That's what it is. And what surface have we found? Well, it's not the catenoid, and it doesn't look like a disc. What is it? In fact, it is a Mobius strip. So this is a picture by M.C. Escher of the Mobius strip. If you watch these ants as they go around, they seem to start up on one side, but then they end up on the same side that they started. The Mobius strip is this beautiful surface that has the property that it only has one side. So these ants, they look like they're on different sides, but in fact, they're all on the same side. And that's what this soap film is. It's a Mobius strip. Okay, so the point of this is that the surface that I get, the soap film that I get, how complicated it is related to how complicated the knot is. So for example, if I take the unknot, then I get a very simple soap film that bounds it. It's just going to be a disc like that. But there are many other discs that also bound the unknot. For example, I could deform it like that. I could just sort of push it up a bit. So how can I, starting from this deformed disc, transform it so it becomes the flat one again? That's the challenge. And once I do that, if I can do that, then I have found the simplest disc that could bound the unknot. And then if I could do this for many, many knots, then I'd be able to shed light on this slice ribbon problem. But what is the mechanism? How do I make the area smaller? How can I do that? That's what I need to do. But nature already does this. And you know this if you've ever blown soap bubbles. If you blow a soap bubble, then you see that when it first leaves the little contraption here, it's not a sphere, it's some weird wobbly shape. But if you leave it for long enough, and it doesn't burst, then it will become a beautiful round sphere. And that will always happen. And the reason is because, again, you're trying to minimize the surface area. And if you do that, you'll always get a nice round sphere. And so that's the mechanism we want to use here. In fact, it is basically the same or very closely related to the heat equation, the way that heat dissipates around the room, that partial differential equation that I wrote down a few slides ago, which shows how you connect knot theory to lots of different parts of mathematics, in particular to differential equations. So I hope I've convinced you today that knots are a beautiful subject. They are important in mathematics, in other parts of science, both physics and biology. They also connect to art and to literature, and that they connect to lots of different aspects of maths that we see in undergraduate and graduate world and in research. And it's something that truly fascinates me, and I hope it fascinates you too. Thank you very much for listening.